Hello students, this is the Chapter 9 multiple choice review for APST. We're going to be taking a look at the multiple choice questions that you tried to answer on your own, and then I will try to walk through step by step how to do each of those questions just in case you had issues with them. I'm going to try to go kind of fast because there's a lot of questions. The first thing I'm going to do is show you the answer key. Here are the correct answers from questions 1 to 23, and check your answers right now. And you might want to skip forward in the video if you did pretty well for the first couple, but you're not sure about 11 or 12 or something like that. So this is kind of a little guide to help you out. Anyway, so here's the answer key, and now let's get into the questions. All right, for question 1, it talks about an experiment that they ran with mice in a maze, and it talks about the different ways to write the null hypothesis and the alternative hypothesis. And you remember from class that there are some misconceptions that sometimes come up with the null and alternative hypotheses. One big error that people make with null and alternative hypotheses is that they use different numbers. Remember that the null and alternative are supposed to have the same number, like 18 and 18, they're the same number. Here we see 16.5. And 18, so we automatically know that this is incorrect. Both of the hypotheses must have the same number. Another piece of information that you have to know is that the null hypothesis is supposed to be the one that says equal to. In all of them, it has equal to, except for this one. It says the H null is mu is less than 18, so that's definitely not going to work either. The next thing we have to realize is that the null and alternative hypotheses are supposed to be comparing parameters, not statistics. So in all of them we have mu, except for this one. This one has x, and of course x represents an individual value, so this can't be it. We need to be either looking at mu or p or something like that. So we're down to two different choices, and these are a two-sided test versus a one-sided test. How do I know that this is one-sided and this is two-sided? This is two-sided because when I say mu is not equal to 18, that means it could either be greater than 18 or less than 18. So we call this two-sided. And since this says mu is less than 18, strictly less than, we can say that this is a one-sided test. So what we have to do is figure out what in the problem tells us whether it's supposed to be a one-sided or two-sided test. So let's take a look at the problem, specifically at this part. Specifically this part where it says the researcher thinks that a loud noise will cause the mice to complete the maze faster. She came up with this idea, this hypothesis, before she actually ran the experiment. So her guess is that the mice are going to run the maze faster. It's not that before the experiment happened, she wasn't sure whether it was going to be faster or slower. She made the hypothesis, we think it's going to be faster. So mu is less than 18. That means the time is going to be less than 18. In other words, it's going to be faster. It's not going to be, well, I don't know whether it's going to be faster or slower. That would be a two-sided test. Correct answer is D, one-sided test. Okay. For number 2, use technology to carry out a significance test and get a p-value of 0.031. Now remember the definition of p-value, it measures the strength of evidence in support of a null hypothesis. It also helps us figure out whether the null hypothesis is going to be rejected or failing to be rejected. This is a definition from StatTrek. Now, there's one truism in when we're dealing with statistics, specifically with significance tests. If the p-value is less than alpha, we reject. If the p-value is greater than alpha, we fail to reject. So since we have a couple of different alpha values here, we have to go through step by step to try to figure out, or option by option, to figure out what to do. There's one we can cut out right away. Remember that we can either reject H null or fail to reject H null. We never, ever, ever accept H null or HA, right? We either reject or fail to reject H null. Another one that we can cut off is here, because we don't ever make decisions about HA, the alternative hypothesis. We only make decisions about H null, which is the status quo, the prior claim, whatever the case may be. All right, so it's either reject H null at alpha equals 0.05, reject at 0.01, or fail to reject at 0.05. Well, let's see. I know that our p-value is 0.031. If alpha is 0.05, the p-value is less than that, right? The p-value, which is 0.031, is less than 0.05. If the p-value is less than alpha, we reject. So this one looks like it's the correct answer. Let's test the other ones. This is reject H null at alpha equals 0.01. If the p-value is 0.031, that means the p-value is greater than alpha. If p-value is greater than alpha, we're supposed to fail to reject, so this one is not right. We're supposed to fail to reject. For letter D, it says to fail to reject H null at alpha equals 0.05. Well, if 0.031 is the p-value, this number is less than this number. We're not supposed to fail to reject if p-value is less than alpha. We're supposed to reject. So this one is incorrect, so let's cut this one off. Again, this one we're not supposed to be dealing with HA, the alternative hypothesis, and we're never supposed to be saying except. So that's my guide to figure out how to answer question 2. Let's take a look at number 3. In this problem, it's talking about a statistical test being more likely to find a significant increase. In other words, it's talking about the strength of the statistical test. Another way to refer to strength of statistical test is the power. So power is affected by 3 different things. Again, I'm referring to StatTrek for the definition of power. Power is dependent on 3 things. Sample size is one thing that affects power. If you have a larger sample size, the power goes up. Significance level, which is alpha, the lower the significance level, the lower the power. In other words, as significance level goes up, the power level is going to go up. And also the difference between the true value of a parameter and the value specified in the null hypothesis. We can think about this third qualification as basically how different, or the how small of a difference there will be between the accepted value and the value that we find from the evidence, right? The effect size. In this case, it talks about just 2 months of the life expectancy from regular slow walking. So that is a very small effect, or I'm sorry, a very small value or difference between the parameter and the value specified in the null hypothesis, right? So since that is a very small value, the power of this test is going to suffer. So since that's something that we can't affect here, we can't control that here, we're going to have to affect the other 2 things. We're going to have to try to maximize our sample size, and we're going to also have to maximize our significance level. These 2 things have to be as high as possible because we can't change this in this particular case. We can't change the differences in life expectancy. So we can instantly eliminate ones that talk about small sample size. So a very small random sample, we don't like that at all, right? We're looking to try to maximize that sample size. The size of the sample doesn't have any effect on the significance test. Well, we can cut that out right away because it does have an effect. Doesn't have any effect? No way. And also very small random sample? No way. So now we're left with 3 different choices. So it's either going to be a, I guess we're only dealing with 2 choices because here's another very small random sample. Remember, very small random samples, no good. So it's either going to be 1% or 5%. Again, it says here the lower significance level, the lower the power. That means the greater the significance level, the greater the power. So between 1 and 5, I'm thinking that 5 is definitely bigger. All right, moving on to question number 4. Researcher conducts a significance test at alpha equals 0.01 significance level. She designs the study to have a power of 0.90. Now, don't worry, you don't have to calculate power on the AP exam, but you are going to have to try to work with numbers that they give you. So again, we're going to talk about power by referring to StatTrek. A type 2 error occurs when the researcher fails to reject a null hypothesis that is false. We call this a false negative. The probability of committing a type 2 error is beta, this symbol beta, this Greek letter. And the power of a test is equal to 1 minus beta. Okay? So again, the power is 1 minus beta. So they give us power here, which is 0.90, and that's equal to 1 minus beta. Now the question is asking, what's the probability that the researcher will commit a type 2 error? Well, we know the probability of the researcher committing a type 2 error is called beta. So all we have to do is use this formula to figure out what the value of beta is. In other words, I'm going to add beta to both sides and subtract the 0.90 from both sides. It turns out that beta is equal to 0.10. So remember, power is going to be, you could think about it as the inverse of the probability of a type 2 error, right? If the power is 0.90, the probability of a type 2 error is going to be 0.10. If the power is 0.99, the probability of a type 2 error would be 0.01. All right, let's take a look at number 5. I'm sorry that the answers aren't down here, but we can work with this. And there we go, I just pasted it in. Okay, after once again losing a football game, they try to figure out whether people want to fire this coach. They took a simple random sample of 100 alumni, and it turns out that 64 of the alumni were in favor of firing the coach. That's a nice, easy thing to work with. We know that 64 out of 100 is 64%, or 0.64, so that's our sample proportion. So now it's asking what the appropriate test statistic is. And you know that the test statistic in this case is going to be Z, because as you remember, ZapTax tells us that if we're dealing with sample proportions, we're going to be using Z. All right. So that means that all of the ones that involve z should stay, and the one that involves t should go. We're not dealing with the t distribution for this case. So I refer back to the reference sheet, and it tells me that the standardized test statistic is supposed to be statistic minus parameter divided by standard error of the statistic. In this case, we're not sure whether a majority of alumni are in favor of firing the coach, but we are saying we want to know whether the majority, which is more than 50%, are in favor of firing the coach. So if I was making an alternate and null hypothesis for this situation, they would look like this. I would have p is equal to 0.5, the parameter of the proportion of folks that want to fire this person are equal to 0.5. And since I'm looking for a majority, I'm saying that the alternative hypothesis might be that p is greater than 0.5. So that means the statistic is from the sample that we collected, and the parameter is going to refer back to this these two hypotheses. So let's look for the ones that are correct. The statistic is supposed to be 64 out of 100, and the parameter is supposed to be 0.5. Most of these are in the correct order. However, I see that letter E is incorrect. That's 0.5 minus 0.64. So we have 1, 2, 3 more choices left. Another thing that you should know is that when we're looking at the denominator of this test statistic, it's supposed to be referred to as the standard error of the statistic. Now, I want you to be careful because the standard error of the statistic is calculated in a slightly different way for significance tests than it is for confidence intervals. Now, keep in mind, this is not on the formula sheet, so this is something that you sort of have to know. This part, we already know, the p hat minus p null. This p null refers to the accepted value of p, the proportion. We already did that. That should be the 0.64 minus 0.5. But the denominator, the standard error, has to have the values of p null. In other words, it has to have the accepted values of the population proportion in there instead of the sample. So these two values should be 0.5, right? That's 0.5 from the h null, which means this one is correct, this one and this one are both incorrect. Another reason why this one, letter D, is incorrect is because the denominator of the denominator, weird thing to say, is supposed to be n the sample size. We know that the sample size is 100. In this case, it's 64, so that's no good as well. Two things wrong here, one thing wrong here, this one completely correct. So the correct answer for number 5 is choice C. Yes, I realize that this is a little bit different than confidence intervals, but significance tests, as I said, are very similar to confidence intervals with some notable small differences. Let's move on to question number 6. Question number 6, which of the following is not a condition for performing a significance test about an unknown population proportion P? Well, you know the three conditions already, the three assumptions or conditions. All right, you know that they're random, 10% or independent, and normal or large counts condition. We're looking for large enough counts or the population size being normal. We're looking for the samples being independent of each other or each sample being less than 10% of the population, and we're looking for randomness. So let's go through and find the ones that are necessary because we're looking for the ones that are not a condition. Data should come from a random sample. Yes, we do want that, so we're going to cut that one off. Letter B says that individual measurements should be independent of one another. That's true. That's part of the independent condition, so we're going to cut that one off as well. Letter C says the population distribution should be approximately normal. Well, we actually don't need that, right? Remember, the population distribution doesn't have to be approximately normal because we're going to be getting around that by using other conditions, right? Using that p times 1 minus p. N times p and n times 1 minus p being at least 10. So this is something that we don't necessarily need. Let's check the others. Both np and n times 1 minus p should be at least 10. We check that for sure. And then if you're sampling without replacement from a finite population, we want to sample no more than 10%. That's the independence condition, or independent condition, I should say. So that one's definitely out. This one is the one that is not a condition. It's not necessary. We don't need the population distribution to be approximately normal, even regardless of what the sample size is, whether it's large or small. This is not something that we need. So there's your correct answer. For question number 7, the z statistic for a test of h null p is equal to 4 versus p is greater than 0.4 is z equals 2.43. Now remember, typically how we interpret things like this is we draw the normal curve. Remember, a normal curve, not a t distribution. And we're looking for z is equal to 2.43, so that's going to be up here somewhere. And according to the problem, we're saying that HA, the alternative hypothesis, is p is greater than 0.4. So since we're looking at greater than, it's a one-tailed test. That means I'm looking for the area from 2.43 all the way up to positive infinity, which is all this highlighted area here. Now what I have to do is try to figure out what that area is, and in order to do that, I'm going to use my calculator. So I turn to my trusty calculator, and I'm going to use Normalcdf. So I go into Normalcdf. I know that my lower bound for this shaded region is going to be 2.43, and my upper bound is going to be positive infinity. Of course, you know that we use 10 to the 99th. And I don't have to change 0 and 1 because this is a standardized test statistic, which means the mean is 0 and the standard deviation is 1. So it looks like my p-value is going to be 0.007. Or rather 0.00755, right? Round to 5 decimal places for a 5. Since this value is lower than both 0.05 and 0.01, we say that it is significant at both, right? Significant means the p-value is going to be smaller than alpha. Significant means we're going to reject the null hypothesis. So significant at both alpha equals 0.05 and alpha equals 0.01 is my correct answer, right? Since we don't know the value of p hat, I mean, that doesn't mean it's inconclusive, right? Because what we do when we're doing a z statistic is we draw the standard normal curve and identify where the z value is. We don't really think that this is accurate at all. All right, for question 8, which of the following 95% confidence intervals would lead us to reject H null, which is p equals 0.30, in favor of HA, which is p is not equal to, remember this is a two-tailed at the 5% significance level. This question is a little strange for this chapter because it is dealing with confidence intervals. However, this is not as difficult as it might seem. We're looking for H null being p is equal to 0.30. In other words, we're saying saying that the claim is that p, the proportion, is equal to 0.30. So we're looking for rejecting that. In other words, we're saying we don't think 0.30 is possible for the population proportion. In other words, we're looking for a confidence interval that does not contain 0.30. This one contains 0.30. Even though it's on one of the extremes, that's okay. It still contains it. Same thing here, 0.27 to 0.31. It contains it. So that's not it. This interval contains it as well. 29 to 38 contains 30. But this one, 0.19 to 0.27, none of these parts have 0.30. So we would say definitely that if we got this confidence interval, we would be very sure, we'd be 95% confident that 0.30 is not going to be the correct answer. So this is the one that's going to lead us to reject H null. And that means none of these is also incorrect. All right, moving on to question number 9. In question 9, the reason we use T procedures instead of Z procedures when carrying out a test about population means is, well, if you remember from our discussion in class, the only restriction that prevents us from using Z, the thing that makes us use T, is because we don't know the population standard deviation. As soon as we don't know the population standard deviation, which is sigma, we have to use T. So that is the correct answer. That's essentially the textbook reason why we use T procedures instead of Z procedures. Now keep in mind, the general reason is that T procedures are more largely spread out, and they allow us to create confidence intervals and significance tests that are more accurate, rather than Z procedures, which the standard deviation of these Z procedures is going to be always the same, whereas T procedures has a wider standard deviation. However, this question isn't asking about that. This question is saying, when do we use T procedures instead of Z procedures? And that is only based on whether we know the population standard deviation or not. Moving on to question number 10. We're testing H null, which is mu is equal to 10, against HA, the alternative hypothesis, is mu is less than 10. This is a one-tailed test. And it tells us that the simple random sample is 20 observations, so that means my sample size is 20. And since we're talking about means, we inevitably have used the T statistic rather than the Z statistic, and it tells us that its T is equal to negative 2.25. So that means I'm going to draw myself a T distribution. It's not the only T distribution, but it is a T distribution. And remember, the drawing for T curves are a little bit different than the Z curve. I like to exaggerate the fact that it's a little bit more squashed, and the concavity shift is not as viewable. Anyway, the T statistic is T equals negative 2.25, and it doesn't, T versus Z doesn't change the fact that the middle of this distribution should be 0, so negative 2.25 is going to be back here somewhere. And since we're talking about mu is less than 10, that means our shaded region is going to be to the left-hand side. So we're going to have to find the area under the curve here between negative 2.25 and negative infinity. So that means we're going to bring out our calculator again. We're not going to use Normalcdf. This time we're going to use TCDF. So scroll down to where it says TCDF. Our lower bound is -1 to the 99th. That's fine. You could use -10 to the 99th, but that's okay. The difference is infinitesimal. The upper bound is going to be -2.25. So -2.25. Sometimes students forget to put the negative. Please don't forget. And now, instead of identifying the mean and the standard deviation, like in Normalcdf, it only asks for my degrees of freedom. Remember, degrees of freedom is equal to the sample size minus 1. So if the sample size is 20, my degrees of freedom is 19. T-distributions are based on this degrees of freedom. Every T-distribution is going to have a different degree of freedom. Pasting this in, we're going to get a value of 0.01825. 0.01825. And now the question becomes quite simple. This value is between 0.01 and 0.02, so there is our correct answer. Moving on to question number 11, we're doing another t-statistic question here. This t-statistic question is talking about mu is equal to 10, and mu is not equal to 10. So this is a two-sided or two-tailed test. And they also give us the simple random sample of 15 observations, so that tells us that the sample size is 15. Now here's a little tip. It says which values of the t-statistic are statistically significant at alpha equals 0.005 level. So normally what we want to do is try to identify values that are the smallest, right? We're trying to pick which one of these is going to give us the smallest value, because remember, statistically significant means smaller than the alpha. So we're looking for smaller than 0.005. Here's one really easy thing to do right away. I know that this is a two-tailed test, so I'm looking for two different regions, right? We're looking for a t-statistic that's both higher than and smaller than the middle, right? So these three are individual values, right? The A, B, and C are individual values. That's not going to work for a two-tailed test. We're going to need a two-tailed test. In other words, one that has a higher and a lower bound, respectively. So let's figure out which one of these is going to give us a number that's less than 0.005. Good rule of thumb, let's start with the smallest one first. -3.326 and 3.326. This value is smaller, -3.326. That's smaller than -3.286. So let's draw it out. So these are the regions that I'm going to be trying to find their areas. So I'm, again, going to use the calculator's TCDF feature. And one of the only differences between this one and the previous one is that since we have 15 observations, we set the degrees of freedom to 14. So here's our value. It's 0.00249, etc., etc., and so forth. All right, so we're going to use our calculator one more time. Of course, that 0.02498848, etc., that's only one of the areas underneath the curve. So what we're going to do is take that number and multiply it by 2 to represent the fact that we're finding this area as well. We could also use TCDF to find that area, but since a t distribution is symmetrical, just like a z distribution would be as well, that means this area is going to be exactly the same. So we're going to multiply this by 2, and we should get 0.0499. Wow, that's really, really close to 0.005. But we know that it is less, right? This number is smaller than 0.005. So that is the value, or these are the values, I should say, that are statistically significant at alpha equals 0.005. There's our answer. Just to quickly show you why this is not correct, if we were to use these test statistic values in the TCDF function, we would multiply this number by 2 and get 0.0054, which of course is larger than 0.005. Slightly larger, but larger nonetheless. Okay, great. For number 12, after checking that the conditions are met, which is something that you always got to do, you perform the significance test of mu equals 1 and mu is not equal to 1. This is, of course, a two-tailed test. And we get a p-value of 0.022, which means each of the individual areas in the lower and upper regions are 0.011, respectively. So this is how it would look if you drew it out. Once we know that the p-value is 0.022, and we know that we're testing mu is equal to 1, this is going to form the basis of our answer here. Which of the following is true? Well, we're doing the significance test for mu is equal to 1. We're not doing a significance test for anything else, any other values. So we're not doing the significance test comparing 0 at all. So let's cut off all the ones that say 0 first and foremost. It's not this one, and it's not this one. Now, we can determine that if the p-value is 0.022, then this is the, I guess, likelihood or unlikelihood that we find a value that is less than, that is not equal to 1. So a 95% confidence interval will include the value of 1. Well, we have a lower value for p than the alpha value for this 95% confidence value, or confidence interval, I should say. In other words, this is saying that the evidence that we collected is strong enough to say that it is not likely that our 1 is going to exist in a 95% confidence interval, because this value, the p-value, is less than alpha. In other words, we are rejecting the null hypothesis. We're rejecting this value of 1. So A cannot be correct. However, with letter C, it says a 99% confidence interval. We know that a 99% confidence interval corresponds to an alpha value of 0.01. That value is smaller than p. In other words, the p-value is greater than alpha, which means that the value of 1 is still possible. We fail to reject the null hypothesis, so the value of 1 could still be the value of mu. So that means our 99% confidence interval would be wide enough that it does include the value of 1. So our correct answer is choice C. It's only based on the idea that if it's a 99% confidence interval, that means the alpha is equal to 0.01, and the p-value, the probability that we get a 1, is higher than that exclusion value. None of these is necessarily true. Get out of here. Nice try, trying to confuse us. Question number 13. Vigorous exercise helps people live several years longer on average, which is great. The added life expectancy is just 2 months. We remember this sort of question from before. As a matter of fact, upon closer reading of this question, it looks like it's the exact same question. So it's based on a very large sample and the 5% significance levels used. So that was a freebie. You're welcome. Question number 14. The most important condition for sound conclusions from statistical evidence is, inference, I should say, is that, well, a lot of students stop at the most important condition, which is something that we do definitely have to consider, right? However, what we're looking for is an important condition for sound conclusions from statistical inference. In other words, we're trying to draw a conclusion about a certain population based on the data that we collected, which means that the data that we collect has to be representative of the population. We could collect, 100,000 data values, a sample of 100,000, right, which is a very large sample size. We could collect it from an exactly normal population. We could collect it from, information that has no outliers. We could make sure that the sample size is, as big as it can be and smaller than 10% of the population size. But if we collect data in a flawed way, if we collect it in a biased way, or we use a sampling method that's, convenience or something like that, if we collect the data in the wrong way, then we can't use that data to draw sound conclusions. So the most important condition for sound conclusions is that the data comes from a well-designed, random sample. We talk about well-designed being like we're sampling so that our sample is approximately the same proportions of the population, right? Random sample, so we either use simple random sampling, stratified, systematic, cluster, that kind of thing, or a randomized experiment. If we're doing an experiment, we have to make sure that we randomize the treatments, and double blinding, all of those good statistical things. So before we do any of the actual math and before we check any of these conditions, we need to make sure that the information, the data that we collected, is sound. It's not biased in any way. That's the most important condition for drawing conclusions. Moving on to question number 15. So we're looking for whether people favor banning ownership of handguns. The commentator believes that more than half of all adults favor such a ban. So we're looking for more than half in the alternative hypothesis. So the alternative hypothesis, looks like we're missing some symbols here. Oh, I know why, because the computer writing program couldn't figure out what p hat is supposed to be. Well, this is supposed to be p hat, this is supposed to be p hat. Since p hat is not the parameter, we're going to cut that one right off. Looking at all the other ones, it looks like the parameters are correct. We're looking for more than half. So more than half would be h null would be equal to 0.5, and the alternative hypothesis would be greater than 0.5. So this one looks correct. In this one, we have less than 0.5. That one's no good. In this one, we have an h null that's not equal to. That's no good. And in this one, we have not equal to 0.5. That would be either more or less. In other words, it would say the commentator believes that it's a different number than half, not more or less. So that one's not right either. Correct answer is choice B. Moving on to question 16, you're thinking of conducting a one-sample t-test about a population mean using a 0.05 significance level, which is pretty standard. It doesn't make you special or anything like that. Everyone uses 0.05 nowadays. You suspect that the distribution of the population is not normal. Uh-oh. And it may be moderately skewed. Uh-oh. Which of the following statements is correct? Well, remember, the central limit theorem says that we are able to sample from a non-normal, skewed, any other crazy population, and as long as our sample size is large enough, we should be able to get a sampling distribution that is normal. Here's that central limit theorem thanks to StatTrek. Thank you, StatTrek, for being so useful. It tells us that any sampling distribution is going to be normal or nearly normal if the sample size is large enough. So what we're looking for is a sample size that is large enough, and there not being any outliers, for us to use a normal assumption, right? So you can safely carry out the test if your sample size is large and there's no outliers. That's going to be your golden ticket here. This one says you shouldn't carry out the test. No way, right? Remember, population not having a normal distribution doesn't matter. CLT is going to fix that. You can safely carry out the test if there are no outliers regardless of the sample size. Well, it's possible that there are no outliers, but there's not a normally distributed population, right? We don't want to deal with a sampling distribution that's not normal, and normal means we need a large enough sample size, so that's not good. Population standard deviation is known. This is going to allow us to use Z, but we can't use Z unless the sampling distribution is normal. No good. And the T procedures are fairly robust, except that doesn't mean you can use them anytime you want. Robust just means they're going to be able to be used in different scenarios. So it's not just anytime you want, there's definitely still some conditions. Moving on to question 17, to determine the reliability of experts who interpret lie detector tests. They did a random sample of 280 such cases. Good thing that it was random because that satisfies one of our conditions. Here are the results, innocent versus guilty. If the hypotheses are H null, the suspect is innocent, versus HA, suspect is guilty, we can estimate the probability that the experts who interpret lie detectors tests will make a type 2 error. Remember what type 2 error is. And remember, type 2 error is a false negative. In other words, they come up with fail to reject when they should reject. In this situation, we're going to be calling reject guilty, so we'll rewrite it a little bit so it makes more sense. In other words, it's innocent. They come up with innocent when the person is actually guilty. Well, these are all the outcomes in which the person is actually guilty, right? Their true status is guilty. So these are all the outcomes that we're dealing with. 125 and 15 is 140, so that should be the bottom, the denominator of our fraction. So it's not 146, it's not 280, and it's not 280. It should be either C or D. And remember, we're looking for fail to reject, or in other words, we find the person innocent when they're actually guilty. Well, remember that innocent is the top row, so these are the folks that they found innocent. There's 15 of them, and there's a total number of 140 of them that are actually guilty. So these are the ones that made the type 2 error. In other words, these are the ones that the person was actually guilty, but they found the person innocent. Okay, great. That was question 17. Moving on to question 18. Significance test allows you to reject a null hypothesis, H null, in favor of an alternative at 5% significance level. What can you say about significance at the 1% level? And this one's real simple. Remember that rejecting a null hypothesis in favor of an alternative, HA, at 5% significance level, all that means is the p-value is less than alpha. Now, since it tells us that we're rejecting the null hypothesis, that means this p-value is going to be something smaller than 0.05. Well, it could be 0.04, 0.03, 0.02. So it's very difficult to say whether we're going to reject or fail to reject the 1% significance level, right? Because we don't know what the value is in compared to 0.01. Of course, the p-value could be 0.000001, or it could be 0.049, right? Either way, it's going to reject the null hypothesis at 5%, but we don't know what it's going to do at 1%. So let's go through and make sure that we're understanding what's going on here. H null can be rejected at the 1% significance level? I don't know, because the p-value could be higher than or smaller than 0.01, so we don't know that. Insufficient evidence to reject H null at 1%? Well, we don't know whether the p-value is higher than or less than 1%, or 0.01, so we can't say that either. Sufficient evidence to accept H null? You gotta be kidding me. Get out of here. HA, the alternative hypothesis, can be rejected. We don't reject HA, the alternative hypothesis. We never touch the alternative hypothesis. Nice try. Letter E says the answer can't be determined from the information given. Unfortunately, that's our guy. All right, moving on to question number 19. And in question number 19, it's similar to a previous question that we did. We have 100 likely voters. We have 59 in favor of candidate A, which means that our sample proportion should be 0.59, and our null hypothesis is p is equal to 0.5. So let's go through and identify the ones that are definitely wrong first. Remember, we're supposed to do p hat minus p, so it should be 0.59 minus 0.5. This one's no good because of that. And this one's no good because of that as well. And remember that the denominator of the z statistic should have 0.5 and 0.5. Here's 0.5 and 0.5. It should have p null. It should not have p hat in it. So this one's no good. And then last but not least, we got a z and we got a t. Since we're dealing with proportions, zap tax kicks in. Zap means we're using z and not t. Easy pickings. All right, number 20. A researcher claims to have found a drug that causes people to grow taller. Sign me up. So they do this test where they pick 1,000 students, which is quite a lot. After they look at those 1,000 students, they only select 50 of the volunteers to be used. Their heights are measured and they're given the drug, and then they find their heights again. We're trying to increase the power of the test. And remember, the power of the test is affected by a couple of different things. Remember that it's affected by sample size, significance level, and the difference between the true value and the value specified in the null hypothesis. So in this case, we're looking at an average increase in height of 1 inch, right? So that's the sensitivity that we want for our test. That corresponds to this last part, which is the difference between the true value and the value specified. The difference is height of 1 inch. We can't affect this. In this case, we're looking for this difference. So this is something we can't affect. So the other two things that we can affect are the sample size and the significance level. So the first and easiest way to do it is to increase the sample size. We have 50. Let's try to increase it to 100. This doesn't help us because only volunteers from the basketball team means our data would be biased. So that's no good. This says this is affecting the sample size, but this is 25 rather than 50. That's no good. We want the sample size to be bigger, not smaller. And then for the second one, significance level, we want it tells us that the lower the significance test means the lower power, which means a higher significance level, higher power. So I don't want to use 0.01 instead of 0.05 because that's smaller. However, using a larger significance level is going to mean a higher power. So C is the correct answer. Let's look at E for a second. Remember that the experiment was looking to see whether the drug causes people to grow taller. So that means our null hypothesis is going to be probably that the difference is equal to 0, right? Because we were assuming that it doesn't cause people to grow taller. But the alternative hypothesis is going to be that the mean height of these volunteers is going to be bigger, greater than. Using a two-sided test doesn't make sense in that case because we're not trying to see whether the drug makes people smaller, for God's sake. So that one's no good. Moving on to question 21. We're looking for a 95% confidence interval. Again, we're looking at confidence intervals here for a population mean that has these values. Assuming the conditions are met, what conclusion can we draw for this test? Mu is equal to 2 versus mu is not equal to 2. Of course, this is a two-tailed test. And now it's lucky that this is a two-tailed test because what they did at first was they made a confidence interval, which by its very nature has to deal with a upper bound and a lower bound. So a 95% confidence interval sort of is very closely related to a two-tailed test at the 0.05 level. So we have our confidence interval being 1.7 to 3.5, which of course includes the value of 2. That means the 95% confidence interval contains that 2 value. So since the 95% confidence interval contains 2, we should be 95% confident that the true value could be 2. In other words, I'm not going to reject H null. I'm going to fail to reject H null. I don't have any evidence to support not believing that 2 is there. I, in fact, have evidence to support that 2 is there, right? It's true that confidence intervals and significance tests are different procedures, but they are not unrelated. They're based on the same concept, right? So C is definitely not true. It also tells us here that we can't carry out the test without the original data. Well, we can definitely see how 2 is within this interval from 1.7 to 3.5, so that's not true. And it says we can't draw a conclusion at 0.05 since the test is connected to a 97.5 confidence interval. That's not true because it says a 95% confidence interval. That 97.5, they're trying to trick you because they're trying to make you think of one-tail test, which is only 2.5%. But of course, this is a two-tail test, so that is not related. Question 22. In a test of H null, which is p is equal to 0.4, against HA, which is p is not equal to 0.4, this is the proportion, and this is a two-tailed test. And the random sample of size 100 means we have a sample size of n equals 100. It gives us the test statistic of z is equal to 1.28. So let's draw out the z curve because it's looking for a p-value, so we'll draw out the p-curve and then figure out where the area under the curve lies. So here's my normal curve with the two boundaries, and I know what you might be thinking. They only found the test statistic of z equals 1.28. Well, remember it's a two-tailed test. That means that 1.28 and negative 1.28 both have to be present. Now we're looking for the area under the curve back here, and we're looking for the area of the curve up here. So that means we're going to be using Normalcdf twice. Or I might be able to use a shortcut. Normalcdf with the lower bound being negative infinity, the upper bound being negative 1.28. I'm finding this area here, plugs it in, and it gets 0.10027. Let's write that down. And of course, if this value is 0.10027, this value is also 0.10027. Let's get that p-value by just taking this whole exact number, this whole precise number, and just multiplying it by 2. Now we'll round it to 0.20055. So if this is my p-value, we're looking for the p-value of the test being approximately equal to something. Seems like 0.20055 is pretty close to 0.20. So let's mark that up. Not with a highlighter, but with a pen. Boom. Okay. Next, but certainly not least, is question 23. We got a simple random sample of 100 postal employees, finding that the average time the employees had worked at the Postal Service was 7 years, with a standard deviation of 2 years. Okay, so we have a mean and a standard deviation. We're looking for the data either providing convincing evidence or not providing convincing evidence that the mean time has changed from 7.5. That was true 20 years ago. So it seems to me that this 7.5 is the accepted value. We could also refer to it as the claim. And the 7 years, that seems like it's the evidence, right? It's from the sample. So in order to answer this question, to determine whether the evidence is convincing or not, let's set up our significance test. Here are the first two steps of the significance test. We've stated that our null hypothesis is 7.5. That's from the claim. And the alternative hypothesis is that mu is not equal to 7.5. I'm using not equal because it says the mean has changed. It already tells us this, but it's nice to know that we're able to figure it out just from the text of the problem. And then in the plan, we're telling the folks that we're using a one sample t-test. We're using t because this is we're dealing with sample means, and Zaptax kicks in. Random, yes, it says SRS right here. Independent, yes, there's more than 1,000 postal employees. That's how the mail gets delivered. And then normal large counts, yes, 100, which is the sample size n, is greater than 30. All right, let's move on to the do step. In the do step, we're calculating a standardized test statistic. In this case, it's t. Statistic minus parameter is going to be 7 minus 7.5. And then the standard error of the statistic is s, which is the sample standard deviation, which is 2, right? Standard deviation of 2 years, divided by the square root of 100, which is the square root of n, right? That n value is going to be 100 postal employees. Calculate that all up, and we get negative 2.5. Since this is a two-tailed test, right, not equal to, we're setting it up using negative 2.5 and also positive 2.5, so we need to find the area under the curve in both cases. Over to the calculator we go. We're looking at negative infinity here and 2.5. Let me scroll down a little so you can see that 2.5. And then my upper value, oh, I'm sorry, this should be negative 2.5. Great. And then I'm using df degrees of freedom being 99 because I have a sample size of 100. So that means that this t distribution is going to be really similar to the z distribution. As the degrees of freedom increase to like 100, 1,000, like larger values, it gets closer and closer to the normal distribution. Now posting this into the calculator, we get 0.007, so that's the area under the curve back here, 0.00703. And since this is a two-tailed test, we're going to take this whole entire value and just multiply it by 2 to get our p-value. So our p-value then is 0.01406. All right, there's our do step, which means I'm up to my conclude step. Comparing that p-value to alpha, we can see that 0.01406 is less than 5, which means we reject the null hypothesis. There's enough evidence to suggest that the time of employment for postal service workers is different from 7.5 years. Okay, so now after all that, after this little mini free response question, let's take a look at what the correct answer is. Now right away we can cut off choice E because we can draw conclusions at 5% significance level. Doesn't matter how large or small the sample size is, get real. There is convincing evidence to suggest, well, I like there is convincing evidence because we started off with there is sufficient evidence, and that's a synonym, right? So I'm liking A, C, and D. There's not convincing evidence, that's no good. That would be what happens if we fail to reject. So let's take a look at A, C, and D. For letter C, it says there's convincing evidence that the mean working time is still 7.5 years. Well, we don't use evidence to prove the null hypothesis. We use evidence to try to disprove the null hypothesis. So we're not saying that 7.5 years is correct. We're saying that 7.5 years is incorrect. So this one's no good. And then for choice D, there's convincing evidence that the mean working time is now 7 years. Remember, 7 is the X bar. It's the sample mean. We're not able to say that 7 is correct. We're just able to say, using 7, which is the evidence, we're able to make the assumption or make the allegation that 7.5 is just not true. So that one's not good either. The only one that we can use is choice A. All right. That was the video on the multiple choice review. Sorry for the long video, but good luck studying.